Hello, everyone, and welcome to another Crypto Watch YouTube video. If you are enjoying this series, please leave a like and subscribe. I'd extremely appreciate it. If you do have any comments or questions, leave them down below. And if you like and subscribe, that would be absolutely amazing. I think I already said that, but whatever. And if you do have any ideas or any other cryptocurrencies that you want me to look into, also leave that down in the comment section below and I will try and answer as much as I can. I am not a financial advisor, so please invest at your own risk. This is for informational purposes only. I just want to bring you guys the best information that I can. Alright, today we're going to be going over the Ethereum white paper. This is pretty long, so bear with me, and yes, I do read everything, so this might be one of those things that would be nice to sit down while you're in the car or just listen to almost like a podcast. So let's get into it. All right, a next generation smart contract and decentralized application platform. Satoshi Nakamoto's development of Bitcoin in 2009 has often been hailed as a radical development in money and currency, being the first example of digital asset which simultaneously has no backing or intrinsic value and no centralized issuer or controller. However, another arguably more important part of Bitcoin experience is the underlying blockchain technology as a tool of distributed consensus, and attention is rapidly starting to shift to this other aspect of Bitcoin. Commonly cited alternative applications of blockchain technology include using on-blockchain digital assets to represent custom currencies and financial instruments, the owner of the underlying physical device, non-fungible assets such as domain names, as well as more complex applications involving having digital assets being directly controlled by a piece of code implementing arbitrary rules, or even blockchain-based DAOs. What Ethereum intends to provide is a blockchain with a built-in fully fledged Turing complete programming language that can be used to create contracts that can be used to encode arbitrary state transaction functions, allowing users to create any of the systems described above, as well as many others that we have not yet imagined, simply by writing up the logic in a few lines of code. Alright, we'll skip over that because that's about Bitcoin, and we are currently going over Ethereum. Alright, Ethereum. The intent of Ethereum is to create an alternative protocol for building decentralized applications, providing a different set of trade-offs that we believe will be very useful for a large class of decentralized applications, with particular emphasis on situations where rapid development time, security for small and rarely used applications, and the ability of different applications to very efficiently interact are more important. Ethereum does this by building what is essentially the ultimate abstract foundation layer, a blockchain with a built-in Turing complete programming language, allowing anyone to write smart contracts and decentralized applications where they can create their own arbitrary rules for ownership, transaction formats, and state transaction functions. A bare bones version of Namecoin can be written in 2 lines of code, and other protocols like currencies and reputation systems can be built in the under 20. Smart contracts, cryptographic boxes that contain value and only unlock if a certain conditions are met, can also be built on top of the platform, with vastly more power than the offered by Bitcoin scripting because of the added powers of Turing completeness, value awareness, blockchain awareness, and state. Ethereum accounts. In Ethereum, the state is made up of objects called accounts, with each account having a 20-bit address and state transitions being direct transfers of value and information between accounts. An Ethereum account contains 4 fields. The nonce A counter used to make sure each transaction can be only processed once. The account's current Ether balance, the account's contract code if present, and the account's storage empty by default. Ether is the main internal crypto fuel of Ethereum and is used to pay transaction fees. In general, these are two types of accounts: externally owned accounts controlled by private keys and contract accounts controlled by their contract code. An externally owned account has no code, and one can send messages from an externally owned account by creating and signing a transaction. In a contract account, every time the contract account receives a message, its code activates, allowing it to read and write to internal storage and send other messages to create contracts in turn. Note that contracts in Ethereum should not be seen as something that should be fulfilled or complied with. Rather, they are more like autonomous agents that live inside of the Ethereum execution environment, always executing a specific piece of code when poked by a message or transaction, and having direct control over their own Ether balance and their own key/value store to keep track of persistent variables. Messages and transactions. The term transaction is used in Ethereum to refer to the signed data package that stores a message to be sent from an externally owned account. Transactions contain the recipient of the message, a signature identifying the sender, the amount of Ether to transfer from the sender to the recipient, an optional data field, a start gas value representing the maximum number of computational steps the transaction execution is allowed to take, a gas price value representing the fee the sender pays per computational step. That was rough for me, apparently. The first three are standard fields expected in any cryptocurrency. The data field has no function by default, but the virtual machine has an opcode using which a contract can access the data. As an example use case, if a contract is functioning as an on-blockchain domain registration service, then it may wish to interpret the data being passed to it as containing two fields. The first field being a domain to register, and the second field being the IP address to register it to. The contract would read these values from the messaging data and appropriately place them in the storage. The start gas and gas price fields are crucial for Ethereum's anti-denial of service model in order to prevent accidental or hostile infinite loops or other computational wastage in code. Each transaction is required to set a limit of how many computational steps of code execution it can use. The fundamental unit of computation is gas. Usually a computational step costs 1 gas, but some operations cost higher amounts of gas because they are more computationally expensive or increase the amount of data that must be stored as a part of the state. There's also a fee of 5 gas for every byte in the transaction data. The intent of this fee system is to require an attacker to pay proportionately for every resource that they consume, including computation, bandwidth, and storage. Hence, any transaction that leads to the network consuming a greater amount of any of these resources must have a gas fee roughly proportional to the increment. Okay, messages. Contracts have the ability to send messages to other contracts. Messages are vital objects that are never serialized and exist only in the Ethereum execution environment. A message contains the sender of the message implicit, the recipient of the message, the amount of Ether to transfer alongside the message, an optional data field, a start gas value. Essentially, a message is like a transaction, except it is produced by a contract and not an external actor. A message is produced when a contract currently executing code executes the call opcode, which produces and executes a message. Like a transaction, a message leads to the recipient account running its code. Thus, contracts can have relationships with other contracts in exactly the same way the external actors can. Note that the gas allowance assigned by transaction or contract applies to the total gas consumed by that transaction and all sub-executions. For example, if an external actor A sends transaction to B with 1,000 gas and B consumes 600 gas before sending the message to C, and the internal execution of C consumes 300 gas before returning, then B can spend another 100 gas before running out of gas. Ethereum state transition function. The Ethereum state transaction function apply STX to S can be defined as follows. Check if the transaction is well formed, i.e. has the right number of values. The signature is valid and the notes matches the notes in the sender's account. If not, return an error. Calculate the transaction fee as start gas, gas price, and determine the sending address from the signature. Subtract the fee from the sender's account balance and increment the sender's nonce. If there's not enough balance to spend, return an error. Initialize gas equals start gas to take off a certain quantity of gas per byte to pay for the bytes in transaction. Transfer the transaction value from the sender's account to the receiving account. If the receiving account does not yet exist, create it. If the receiving account is a contract, run the contract's code either to completion or until the execution runs out of gas. If the value transfer has failed because the sender did not have enough money or the code execution ran out of gas, revert all state changes except the payment of the fees and add the fees to the miner's account. Otherwise, refund the fees for all remaining gas to the sender. Send the fees paid for gas consumed to the miner. For example, suppose that the contract code is, you can look at that if you want to. Note that in reality, the contract code is written in the low-level EVM code. This example is written in Serpent, one of our high-level languages, for clarity and can be complied down to EVM code. Suppose that the contract storage starts off empty and the transaction is sent with 10 ether value, 2000 gas, 0.001 ether gas price, and 64 bytes of data, with bytes 0 to 31 representing the number 2 and bytes 32 to 63 representing the string Charlie. The process for the state transaction function in the case is as follows. Check the transaction is valid and well formed. Check the transaction sender has at least 2000 times 0.001 equals 2 ether. If it is, then subtract 2 ether from the sender's account. Initialize gas assuming the transaction is 170 bytes long and the byte fee is 5. Subtract 850 so that there is a 1150 gas left. Subtract 10 more ether from the sender's account and add it to the contract's account. Run the code. In this case, this is simple. It checks if the contract's storage at index is used. Notice that it is not, and so it sets the storage at index to the value Charlie. Suppose that it takes 187 gas, so the remaining amount of gas is 1150 minus 187 equals 963. Add 963 times 0.001 equals 0.963 ether back to the sender's account and return the resulting state. If there was no contract at the receiving end of the transaction, then the total transaction fee would simply be equal to the provided gas price multiplied by the length of transaction in bytes, and the data sent alongside the transaction would be irrelevant. Note that messages work equivalently to transactions in terms of reverts. If a message execution runs out of a gas, then that message execution and all other executions triggered by that execution revert, but transparent, executions do not need to revert. This means that it is safe for contract to call another contract as if A calls B with G gas, then A's execution is guaranteed to lose at most G gas. Finally, note that there is an opcode that creates a contract. Its execution mechanics are generally similar to call, with the exception that the output of the execution determines the code of a newly created contract. Okay. We definitely have a lot to go over still. So I think at this point we're going to kind of skim through it. So let's go over applications. In general, there are three types of applications on top of Ethereum. The first category is financial applications, providing users with more powerful ways of managing and entertaining into contracts using their money. This includes subcurrencies, financial derivatives, hedging contracts, savings wallets, wills, and ultimately even some classes of full-scale employment contracts. The secondary category is semi-financial applications where money is involved, but there is also a heavy non-monetary side to what is being done. A perfect example is self-enforcing bounties for solutions to computational problems. Finally, there are applications such as online voting and decentralized governance that are not financial at all. Financial derivatives and stable value currencies. Financial derivatives are the most common application of smart contract and one of the simplest to implement in code. The main challenge in implementing financial contracts is the majority of them require reference to an external price ticker. For example, a very desirable application is a smart contract that hedges against the volatility of Ether with respect to the US dollar, but doing this requires the contract to know what the value of ETH to USD is. The simplest way to do that is through a data feed contract maintained by a specific party, NASDAQ for example, designed so that the party has the ability to update the contract as needed and providing an interface that allows other contracts to send a message to that contract and get back to a response that provides a price. Okay, identity and reputation systems. The earliest alternative cryptocurrency of all, Namecoin attempted to use a Bitcoin-like blockchain to provide a name registration system where users can register the names in a public database along other data. The major cited use case is for a DNS system mapping domain names like bitcoin.org or in Namecoin's case bitcoin.bit to an IP address. Other use cases include email authentication and potentially more advanced reputation systems. Okay, decentralized file storage. Over the past few years, there have emerged a number of popular online file storage startups, the most prominent being Dropbox, seeking to allow users to upload a backup of their hard drive and have the service store the backup and allow the user to access it in exchange for a monthly fee. However, at this point, the file storage market is at times relatively inefficient. A cursory look at various existing solutions show that particularly at the uncanny value 20 to 200 gigabyte level at which neither free quotas nor enterprise level discounts kick in. Monthly prices for mainstream file storage costs are such that you are paying for more than the cost of the entire hard drive in a single month. Ethereum contracts allow for the development of a decentralized file storage ecosystem where the individual can earn small quantities of money by renting out their own hard drives, and unused space can be used to further dive down the costs of file storage. Decentralized autonomous organizations. The general concept of a decentralized autonomous organization, or DAO, is that of a virtual entity that has a certain set of members or shareholders which perhaps with a 67% majority have the right to spend the entity's funds and modify its code. The members would collectively decide on how much the organization should allocate its funds. Methods for allocating a DAO's funds could range from bounties, salaries, or even more of a traditional company or nonprofit being used. Only cryptographic blockchain technology for enforcement. So far, much of the talk around DAOs has been around the capitalist model of decentralized autonomous corporation, DAC, with a dividend receiving shareholders and tradable shares. An alternative, perhaps described as decentralized autonomous community, would have all the members have an equal share in the decision making and require 67% of existing members to agree or add, remove, or member. The requirement that one person can only have one membership would need to be enforced collectively by the group. Further applications. All right. All right. Well, I think that was most of it. There's not really too much more that we should go over. We can go over scalability real quick. One common concern about Ethereum is the issue of scalability. Like Bitcoin, Ethereum suffers from the flaw that every transaction needs to be processed by every node in the network. With Bitcoin, the size of the current blockchain rests at about 15 gigabytes, growing by about 1 megabyte per hour. If the Bitcoin network were to process Visa's 2,000 transactions per second, it would grow by 1 megabyte per 3 seconds, 1 gigabyte per hour, 8 terabytes per year. Ethereum is likely to suffer a similar growth pattern, worsened by the fact that there will be many applications on top of Ethereum blockchain instead of just currency, as in the case with Bitcoin, but ameliorated by the fact that Ethereum full nodes need to store just the state instead of the entire blockchain history. So that is Ethereum's white paper. Yes, we did skim over it a little bit. I kind of just picked out the most important things. If you did enjoy the video, please leave a like and subscribe. I'd extremely appreciate it. And yes, Ethereum is something I am currently invested in. Again, it's not financial advice. It is brought to you for informational purposes only. All right, everyone. Have a great one.